Today, on how it's made. Train rails. Desalinated water. Racing wheelchairs. And parquetry. In the early days of the railroad, train rails were made of either cast iron or wrought iron. Cast iron was too brittle and would break easily. Wrought iron was too soft and would wear out too quickly. So steel eventually became and remained the train rail metal of choice. The train wheel's rim runs on the inside of the rail to keep the train on the track. This plant makes train rails entirely out of recycled steel from scrap yards, food cans, and recycled pieces from the rail-making process itself. Electromagnets pick up the scrap and dump it in a charging bucket. A truck hauls the bucket inside, where a crane drops the contents into a furnace. An intense electric current melts the scrap steel at 1650 degrees Celsius. It then flows into a large brick-lined ladle, where they add carbon, manganese, and other elements to make the steel more durable. The alloy then runs down a ceramic tube that shields it from exposure to oxygen, which would ruin the metal. From there, the molten metal flows into molds which extrude it into continuous rectangular blocks called blooms. Acetylene torches cut each bloom into 3.5-meter lengths. A crane then transfers the blooms to a furnace, which, over the next 5 to 7 hours, reheats them to 1250 degrees Celsius. This softens the steel for further shaping. Then the reheated blooms enter a machine called a rolling mill, which elongates each bloom more than quadrupling its length. A shear then slices the longer, thinner blooms into 4 pieces. The pieces now go into another furnace for reheating. This preps them for the next set of rolling mills, which will gradually form them to the final rail shape. Different railroads used to use different shaped rails, which required changing the train's wheels when passing from one railway to another. By the turn of the 20th century, the T-shaped rail became the industry standard and remains so today. For the final shaping, each steel rail passes several times through 3 consecutive mills. This is what a mill's rollers look like. And here's the standard T-shape to which they form the steel. Next, a saw slices off about 30 centimeters to square off the ends. The cut-off pieces go back to the scrapyard. Meanwhile, the rails are laid out until they cool to about 500 degrees Celsius. Then an electromagnet piles them in a holding box, where they sit for 10 hours until they cool to about 90 degrees Celsius. When they come out of the box, they run through 2 sets of rollers. The first set flexes the rail vertically. The second, horizontally. This flexing process straightens out the rails, which curved slightly due to all that heating, shaping, and cooling. Next, each rail passes over a mirror, enabling inspectors to examine the bottom as well as the top. Finally, a saw cuts the rails to whatever size the railway ordered. most often the standard length of 25 meters. The Quality Control Department measures random samples to make sure all the dimensions are precise. Every rail bears a number identifying the batch of steel from which it came. In the event of a problem, that number lets them trace all the rails made from the same batch. It's a system that ensures a safe, smooth ride. In regions where fresh drinking water is limited, desalination plants remove salt from seawater, converting it into fresh water suitable for human consumption. There are more than 13,000 desalination plants worldwide, producing 45.5 billion liters of water a day. The desalination plant that produced this drinkable water is located right next to an electrical power plant which uses seawater to cool down its condensers. Post-cooling, the water travels via underground pipes to the desalination plant. Before salt extraction, the water is pre-treated in a multi-phase cleaning process. First, the water flows through screens which filter out large debris. From there, it flows into basins for the first pre-treatment stage. As large paddles agitate the water, the plant adds two chemicals: sodium hyperchloride, a disinfectant, and ferric chloride, a coagulant. The coagulant binds together sand and other tiny particles of debris, forming heavier clumps that sink to the bottom. This removes a significant portion of dirt from the water, but it's still far from being crystal clear. The water now moves into another set of basins for the second pre-treatment phase, sand filtering. Inside each sand filter, regulated by various pressure and flow gauges, a steady stream of air continually moves sand in a circular motion. The seawater enters at the bottom of each filter and flows to the top. As the sand moves downward against the rising water, the dirt particles attach to the sand. The seawater now looks clean, but still contains microscopic particles. So it enters the final pre-treatment phase. This time, the filtering medium is diatomaceous earth, a powdered rock that contains algae fossils. Finer than sand, it filters out those microscopic particles. The seawater is now perfectly clean and ready for salt extraction. They do that using membranes, cylinders containing layers of plastic sheets that have pores 1/1000th the diameter of a human hair, small enough to trap microscopic salt crystals. The plant pumps the clean salt water under extremely high pressure through long tubes, each of which contains 8 membranes. By the time the water passes through all the membranes and reaches the center of a tube, it's completely salt-free. Plant personnel and a slew of sophisticated instruments continually monitor every one of the system's 10,000 membranes. Meanwhile, the plant sends the debris removed earlier to large waste basins for another round of chemical treatment. After the solids settle to the bottom, the dirty water goes back to the front of the plant to be cleaned and recycled. Pressure rollers squeeze the remaining water out of the solids. Trucks then transport the dry solids to a landfill. The extracted salt, meanwhile, goes to the power plant, which dilutes it, then returns it to the sea in a way which doesn't upset the water's natural salinity level. Processing salt water into fresh water strips away the water's natural minerals. Not replacing them would create two problems. First, the water wouldn't taste right. Second, it would damage metal pipes by aggressively trying to replace the missing minerals. Therefore, the plant adds liquid lime and carbon dioxide to the water. These two elements adjust the pH level and raise the alkalinity, restoring the minerals and natural taste. World War II veterans disabled in combat were the first to race in wheelchairs. But those chairs were clunky steel models. Fast forward to today, and wheelchair racing is a serious sport with aerodynamic chairs. These chairs have elongated mainframes and 3 wheels instead of 4. This modern racing chair is tailored to the athlete's physique, specific disability, and skill level. They begin by taking detailed measurements of the athlete as she sits in a demo chair. They measure the width and height of her knees to determine the best seating position. They check the balance point to decide how the rear wheel axle should be positioned. And they measure her arms so push rims can be sized for her. Then they produce a digital drawing of the racing wheelchair, complete with any extras requested by the athlete. The fabricator selects the appropriate aluminum tubing and cuts it to the desired length. This one will be the main tube for the racing chair's frame. Rollers curve the tube slightly at one end so the framework will accommodate the seat. A press then flattens the tube quite a bit. This stiffens the metal and will make the racing chair frame more aerodynamic. This small tube, which they weld to the main tube, will hold the racing chair's steering fork. He now tapes a steering mechanism to the front wheel onto the framework and confirms that its placement is exact before welding. This device will keep the front wheel on autopilot, freeing the racer's hands to push the rear wheels. The welder now positions the other end of the main tube perpendicular to the wheel axle. He inches the tube towards the center of the axle until it's right on the mark. He welds the axle to the main tube, giving the framework a T profile. Temporary wheels lift the axle so he can install the seat frame. Then, a hydraulic machine bends an aluminum tube into a U shape to make the racing chair's seat frame. He positions the seat frame on the rear axle and does a few more welds. Finally, he installs fenders on the wheels. The main framework of this racing wheelchair is complete. But to make it look flashy, they spray paint it red. This is a powder coating. It's a thermoplastic paint that's tougher than the conventional kind. Next, this machine rolls the push rims, which the athlete uses to propel the wheelchair. They weld on pegs for attaching the rims to the wheels, then glue a rubber sleeve onto each rim. They wrap it in tape to clamp the two as the glue dries. The tape stays on until the chair is delivered to the customer. They install the rear wheels at an angle to make the racing chair more stable when cornering. They add padding for the athlete's knees. Then assemble the nylon seat to the chair. Next comes the front wheel steering fork and handle. They complete the assembly with a spring-loaded cylinder that's part of the steering autopilot system. After testing the steering fork, they install the front wheel, which is smaller than the rear tube. Once it's been equipped with brakes, this custom racing chair is ready to take on the competition. An elite athlete will buy a new racing chair every year. Some choose rear wheels made of lightweight carbon fiber, because any advantage is welcome in the push to win. Parquetry was invented in France in the 1600s as an alternative to high-maintenance marble flooring. It's made from small pieces of wood bonded together in a geometric pattern. The most common motif is squares, but it also comes in other patterns such as herringbone, lozenges, and triangles. Parquetry can be made of laminate or plywood. However, the best quality flooring is made from genuine wood such as oak, maple, or yellow birch. The factory first cuts the wood into planks, measuring 4 to 12 centimeters wide by about a meter long. A drum saw then cuts each plank into 6 blocks about 16 centimeters long, while an inspector discards any misshapen ones. The blocks then move through a planer, which shaves a fine layer off both sides. This reduces the blocks to a thickness of 2.2 centimeters and smooths the top and bottom surfaces. Next, the blocks run through a saw with 10 blades that slice them into strips, measuring 0.8 centimeters wide by 15.8 centimeters long. Quality controllers remove any strips with inconsistent thickness, which are usually the ones cut from the block's extremities. The good strips continue on to another area where they undergo a more thorough quality control inspection. A worker checks the tops and bottoms, then lines them up on a conveyor belt, good side up. She also discards any substandard strips that may have slipped past the first inspection. The conveyor belt then flips the strips over. This positions the strips underside facing upward. Saws then cut 2 parallel grooves through them. These grooves are set 22 millimeters in from the edge and are just deep enough to hold a thin aluminum wire that'll connect the strips together to form tiles. The next machine dispenses the parallel wires. A wheel pushes the wires deep inside their respective grooves. After every 7 strips, the machine cuts the wires and starts new ones. The 7 linked strips form a 15 centimeter square tile. An end-matching machine now squares each tile so that the 4 corners are precisely 90 degrees. Then it carves tongues on 2 of the tile's edges and grooves into the other 2. 4 tile feeders then drop tiles into an assembly machine, which inserts the tongues into the grooves. The machine then applies hot glue, which bonds the 4 tiles into one larger tile, measuring 30 by 30 centimeters. The tiles are now ready for varnishing. Feeders drop them onto the automated varnishing line. The tile surface gets a sanding. Rollers then apply an even coat of varnish. From there, the tiles immediately pass under ultraviolet light. This dries the varnish within a second. Then the process repeats 3 more times for a total of 4 coats of varnish. Workers then stack them in tens, at the same time doing a final inspection and discarding any tile that has a less than perfect finish. On the packaging line, each stack gets a label and clear plastic wrapping. An oven shrinks the plastic tightly around the tiles. Those 4 coats of varnish made this parquetry super durable. And because it's real wood, when the many years of wear do begin to show, you can simply refinish the floor to its original splendor.